Hey everyone, how are we doing? I am streaming with OBS right now, so I'm not using Streamlabs OBS. We're gonna see if there's any issues right here. It's a whole different setup. It's so weird. This is why I'm doing it during office hours and not during regular hours. I've got some of the stream deck set up and we'll see what happens. It's Watch What Happens Live with Brian Stevens using different streaming software instead of Streamlabs OBS. We'll see if there's any buffering issues, so please tell me if you experience any buffering issues. If we have no buffering issues, we need to make the switch back to OBS. But who all is here? I think we're streaming on the internet, right? Are we streaming? Are we on the internets? We've got a few people watching, it says. It looks like we are. I'm just going to mute myself. Quality of picture looks good. I'm going to compare this later on to see if I see any differences here. Hey, Sarah, good to see you. Sarah, tell me if there's any buffering issues. What are you working on, Sarah? You're working on the homework? So if anything, I don't know if we'll crash or anything. We'll find out. Everything seems good. Ryan, awesome. Tell me if it buffers at any point. So tell me if it buffers, because using OBS instead of Streamlabs OBS, we'll find what happens. Dropped frames, no dropped frames, kilobits up, 4 kilobits up. So yeah, I can see all the CPU utilization. Looks like everything's good. We can start doing some homework assignment here. Who wants to do some My Pearson assignments? Let's get My Pearson up and going. Assignment manager. Let's look at the latest assignments we have coming due. So the next assignment is chapter 14, homework and quiz. Whatever people want to do, it's your office hours, it's your call. What do people want to do right now? We could do confidence rolls. We could do sampling distribution of the sample mean. Whichever homework problems you're working on, your call, your office hours. Say, hey, Brian, can you work on the visualization? Hey, Brian, can you work on this homework? Can you work on this quiz? You got it. Can you explain this concept? Whatever you want to go over. Let's try to get some 100s here. Can I play my music? I can still play my music, right? I didn't break everything. Chill music. Gonna get that second cup of coffee soon. It's... Yeah, it's stats, yeah. What are you working on, Ryan? It's just office hours. It's everyone's call. Your call, your say, hey Brian, can you explain this? Can you go over this? We try to distribute everything evenly. But we did what did we do this morning? We did visualization this morning, and then we did assignment number 9 for 320. So this morning we did the visualization, so the next visualization that's due Friday. And then we did, yeah, you're 320, right? So I think you're saying is it stats like stat to 1. It's 320, it's anything. There's just open office hours. Especially right now, there's no questions. I'm just looking up at OBS being like, are you going to crash? You can do something weird. Looks to be going fine. Looking at the music from the Go XLR. Assignment 8, part 2, you got it. Let me go grab that. You bet, Ryan. Which part are you working on with that, Ryan? If you want to say which part you're working on, we will do that. Assignment 8, part 2. Just listen to some music, yeah. And let me know if there's any buffering. Why are you buffering tonight? Some Julian Smith. What if I could play just a second of that? Like, wow. I'd get hit with a copyright claim. It's so easy to get hit with copyright claims. Don't want copyright claims. Okay, Ryan, we got this. Do I have the button set up to work on here? Let's find out. I do, but I'm not here. What? I don't exist in this world. 2 seconds. Why don't I exist over here? Let me go bring Brian to this world. I think I can fix this. Where am I? Wait, I turned off there. Okay. 2 seconds. I'm using OBS, so I'm... Okay. This should do it. Hey, there I am. This shouldn't have a problem. Whee! Go over here to the corner. Grab the edge of this. Bring that in. And there we go. Look at that. Nice and neat. Fix it live. That's how we do it. Okay, so can't get the model hierarchy to work correctly. Also, my visual looks really weird. What variables do you have in the model here? What variables do you have in the model? Let's go ahead and remove all this. Let's go here and we can run the top of this, which will bring in the data. I'll be looking at this later, seeing if it worked really well. Cool. So now we've got the sample loaded in. We've got my sample, which is just our data. And yeah, we're good. I'm just going to play some nice music. What model are you building, Ryan? And tell me if there's any buffering. There's the... Did my music not play? Got right here the model. It looks to be... so yes. I know why it's looking weird. So what is the format? Oh, God. Wrong button. So what is the format when we build... I did a thing that I haven't done for years. Maybe not years. What is the format when we build a formula for a confidence interval? We have a classic formula. Blank, blah, blah, blank, blah, blank, blank, blank. So here is the formula. Y tilde x comma data equals whatever. So there's the formula right here. Y tilde x comma data equals. And do you see the issue? We can separate this out a little bit here. There's the y tilde x comma data equals. So do you see the issues right here with this? I bet this will look pretty interesting. Oh man, let's see what we get. Oh, and it's given, what's it saying here? It's not happy about something. So that might be part of the issue. Whoa, that looks so cool. I mean, not cool in a good way. We'll fix it though. Oh my gosh. Yeah, you don't want to turn this in. You don't want to be like, I love seeing this though. It's so cool to look at. It's really weird what's happening here. And I'm actually, one of my goals is to improve this over the summer. I've just never had enough time to go in and make some changes here into the way these work. So the issue is it's not written y tilde x comma data equals. So let's take the y tilde. Here's your x's. So we're going to put this as the same format. There's y tilde x. We're just kind of putting it on separate lines. Comma data equals. And now we rerun it. And it's giving a weird error message. What's going on right here? Oh, you're using an x variable to predict the x variable, which that's doing a weird error I've never seen, but don't worry. So this right here is using average wind speed to predict average wind speed. So we don't want to do that. For this one, pick two quantitative variables and create a model with the interaction. Explain why your model creates a model hierarchy. So I think we're predicting demand. So in this data set, we're predicting demand right here. You'll get the same problem. If we go down here and we do this, we'll see the same sort of crazy. Oh, it's so cool. I just love seeing these graphics. It's I don't know. I just think it's beautiful. That's very interesting. But what we want to do is we want to predict demand. And there we go. Does this make more sense right here, Ryan? Is everything clear? Have we not buffered at all? If we don't buffer, I'm going to be like, oh, maybe this is the solution. Yeah. So we're going to predict demand right here. We don't want to use a y variable to predict the y. Has everything been really smooth right now, Ryan? No buffers? I also think the video is smoother. Darn you, OBS. Why are you better than Streamlabs OBS? Making me switch back. Gotta get everything set up. Gotta redo it all. I did see a buffer, though, on my side. And I was like, really? This is going to buffer too? It says we're going 4,000 kilobits up, though. It's kind of like it shows that. No buffers. No buffers. Good stuff with that. So, and then what else were you wondering about? And then the model hierarchy. We should preserve model hierarchy. And talking about model hierarchy here, how do we know we've preserved model hierarchy? Let's look at the model. And why have we preserved model hierarchy here? Why is model hierarchy preserved? Look at this. And then look at above it. So what does it mean to preserve model hierarchy? And why have we preserved model hierarchy here? Now the hierarchy is good. Yep. I wonder, you know what it might have... I think previously... I bet you it doesn't let you put in the Y. Yeah, model hierarchy is broken because it doesn't let you put in the individual variable. Because average wind speed is the Y variable, so it's not letting you put the Y variable as an X variable, but it lets you put the interaction. So this doesn't preserve model hierarchy, and this I wouldn't make this model because you're using the Y variable to predict the Y variable. And you can do stuff like that if you're doing an auto-regressive model. There's things that do stuff like that. We predict like the last period and use the y variable to create a variable. But we're not doing that right now. Some statistician jumps into the room. What? I ran the whole thing by accident. There we go. And you don't have to break it up like this, but you can if you want. But that should show you the code right there. Y tilde x comma data equals y tilde x comma data equals. And the average temp and average wind speed are included separately before the interaction smile hierarchy is good. Yep. That's what we see. I need to increase this screen size. There we go. Yep. It doesn't... I think it'll always include them before, just the way it does it. You could technically include them before. Like, it doesn't matter the order. You really have to work to make it include them. The coefficients should be the same. This is just a long way of doing it. Oh, and it won't. I can't get it to include it in a different order. It's always going to put this one right here. So as far as I can tell, I can't get it to not do that. Yeah, I really, unless, yeah, I don't know how to get it to not do that. So yeah, but it's totally fine. It doesn't, I guess it just makes sense to it and the model that it would do it in that order. It would do it in that order. Great answers right there. Great stuff. I'm trying to think what else. There's something a long time ago. Let me see something, because this will go to this week. So if you have questions, let me know. Keep asking questions. I'm going to look up something. Do we use the extrapolation check? You can. So if you're thinking about extrapolation check right here, one thing to look at is, let's do a summary of the model. And we can take certain variables here. So if you want to look at your x variables to think about when you'd be extrapolating, we can go right here. We can put the names of the columns. So please note that what I'm doing is I'm doing a summary. I'm taking only the columns right here. Let's look at this in little bits. Little bits. Right here, we have a vector of just the names of the columns I'm interested in. The vector of the names of the columns is going into a data frame. So this is just a data frame, and we're going to thus take only those columns. And so then when we take only those columns, we're then going to take this whole thing right here. Like, this might as well just be called X. We just call that X. All we're doing is just doing a summary of X. And we're doing a summary of the columns. Like, you could also just call this right here, like, names. And so the names are the names of the columns we are taking. And then we're going to do a summary of that. So if you put the whole thing together right here, you'd be doing a summary from your sample, and you're going inside of it, and you're going to take concatenate, and then we'll just copy paste this, because that's a lot to write. And that'll give you the same output. So everything we're doing right here in multiple steps can be done as just one big thing right there. So then we would see that average temperature, which is an X variable, goes from 4 to 35, and this is in Celsius. Wind speed, which is in miles per hour, goes from 1.5 to 34 miles per hour. So if you're outside of this, you are extrapolating. And so if we go right here and we make a data frame, we store a data frame into it. And we're going to go right here, and we're going to take the variable average temp. We can take a value for average temp, a value like 3. And then we go here, put another variable. We do comma to do another argument. And then we go right here, and we do an average temperature of 1. We go to extrapolation check, and we put in our model, and then we put in our new data equals df, and we can see that that is in the 99.8th percentile. We can make it more extreme right here. If we go to a wind speed of like 100 miles per hour, we'll get the 100th percentile. So this tells us where we're doing extrapolation at, which now we're not extrapolating as much as we move towards the mean of the data. 50% is not the mean. The mean of the data would be at 0th percentile. Like how far you are out from the center of the data, and we can confirm this by going to the mean of the x's right here and seeing that when we extrapolation check this, we get the following. So this would be an extrapolation check right here, and this would say we're at the center of the cloud of our data. So visually speaking, what have we done right here? Well, when we're doing a bivariate extrapolation check, because we have two x's, we're actually asking what is the x space of our data. We have here x1 and x2. This is not an xy plot. And our x space of our data might look something like this right here. And the idea of extrapolation check is the following. At the very, very center of the means of our x's. Because this would be like x bar 1 and x bar 2 if we talk about where they intersect right here. At the very, very center of this cloud of the x's, what percentile have we gone outside of it? So Ryan, what percentile have we gone outside of the x space of our data? Going outside of the x space of our data right here, what percentile have we gone outside of it? And I'm going to do a really cool plot, I think, next. If you're 201, 320, feel free to ask questions, because I'm going to just do some fun plot here in a moment next. So we're at the very, very center of our data there. The very, very center of our data. The very, very center of our data. What percentile have we gone outside of it? What percentile have we gone outside of it? Zero. Don't worry, Ryan. Great job right there. We'll throw some 50 points. Zero. That would be the 0th percentile. So at the very, very mean of all the data, and here I'll explain to you what we have right here because I've done it in R also. Great job right there, Ryan. Don't worry. This is just the time to learn. This right here is the mean of the x's. You see how I was able to find the mean of the x's right here. So at the mean of the x's, which are the values I input for average temperature and the values I input for average wind speed, when I do an extrapolation check, it tells me I've gone 0% outside of it. But the reason I'm doing the color coding right here is because the further out you are, the more you're extrapolating. And frankly, I should have a darker color red to go when you're outside all the data. We'll go here to like gray, which means we've super extrapolated. Now we're in the 100th percentile. Anything outside of here is in the 100th percentile. So extrapolation is a matter of degree, because you can see you could head, like if we take a path right here, if we start going away from the mean of the x's, you could start going this way a good bit, and you would not be extrapolating as much if you were to then, in turn, go the same thing, but you were to go like this way. If you were to go perpendicular this way, you'd have extrapolated completely outside of the bounds of your data. So this is why we have to think about the bivariate sense of the combination of the x's, because like what is the combination? Is the combination unusual? Because this is not that high in x1 and it's pretty high in x2. That's a pretty high x2 value. It's slightly low in x1, but it's extremely odd value. Does that make sense, Ryan? Like this would be an extremely odd value to be predicting from. But right here is a high value. Like this is not too odd. It's maybe in the 80th percentile. But over here, if we use this same distance in terms of actual, like, I can't think of the name of the distance, Euclidean distance. I think it's Euclidean distance right there. In terms of Euclidean distance, we would have the same Euclidean distance, but we've now gone outside of the bounds of the x's because it's an unusual combination of the x's, and that's where you're extrapolating because your model is not predicting, it doesn't have x data in that sense. Is this making sense, Ryan, here to talk about, like, it's not just are we extreme on one x here, because we're not extreme on either x. We could make this even smaller here, so we could reduce it till that's extrapolating. So now your x1 is a little bit low, your x2 is a little bit high, but you are extrapolating. But if you were to just change the way you're doing this, well, then now you'd be kind of in the 40th or 50th percentile. So anything outside the max, the variable would be 100. Well, so maybe not, because watch this. What if, and this is where things get really interesting in the multivariate world, what if we were to say that this one right here is at the mean, but this one is at the max? That would be the 100th percentile. Yeah, maybe so. Maybe so. That's at the 95th percentile, and that's below the mean. So that's below the average. So this right here, this combination of x's, you are extrapolating in the univariate sense on this. Like this is an extrapolation of average wind speed, but in terms of the multivariate x space, there are things further out in terms of a multivariate combination. So there is the idea of multivariate like combinations of x's, and there's this x. This is where it gets just a little bit complicated, because we're not just talking about these two, we're talking about the multivariate x space, which actually looks like, here we can make it really quickly with this. We can cheat. The multivariate x space we have looks like this. Here's the multivariate x space. Really, really weird multivariate x space. So this is the multivariate x space we have. And Here we can see where we were at. This one right here is the 95th.1 percentile. So let's figure out where this is at. AB line, we want average temp. So that's going to be horizontal. H equals this. Col equals red. Good. And then wherever this intersects. So then we go here and we go AB line. V equals 1. Col equals red. And that's where we are right here. It looks to me like these out here, like if you think of the density cloud that we drew, drawing your density cloud with eigenvectors and eigenvalues, which, sorry, we don't need to get too complex. We're not doing linear algebra right now. But drawing the density cloud, I can see. I'm just going to throw the pen. Ah, my mute button works on me, actually. That's awesome. I actually made the buttons. Drawing your density cloud out from this, it looks to me that there are some points still outside of this. Like, the points that are showing up are probably these points right here. 1, 2, 3, 4, 5. 5 points are more extreme than our point, and the data frame has 400 and that many observations. Maybe it's a little bit more than that. It is a little bit more than that. Is this making sense here, Ryan? What's going on? That when we look at this, here's our prediction right here, but there seems to be some points that are more extreme. Like these points over here are more extreme than this one in their multivariate X sense. So these points over here, even though this is outside the bounds, because you look, it's inside the bounds of average temperature. It's actually at the mean of average temperature, but it's outside the bounds of average wind speed. But these ones over here are more extreme. Like this is probably the most extreme point right here. So if we were to go right here, or if we just change this to like 34, so let's change this to 34, we'd be, oh, wait, wrong one. We need to change this over here to 1 to 34. This needs to change to 34. There we go. And let's change it to 33. There we go. My guess is that this is going to be 413 divided by this. It's going to return this for the answer if we change this to 33. Whoop, there we go. Yes, this is the same answer. That is 99.8. Is this, so this point right here, if we make a prediction right here, in terms of the X space, there's only 1 point more extreme than it. And I think it might make more sense if I drop it down so it's right near it, so you can see it in line with it. But there's only 1 point further extreme from this. Does this make sense right here, Ryan, that making a prediction for this right here, if we use the model to predict right here in terms of the X space, we only have 1 more point because there would be 413 points within kind of the X space, and there's only 1 point more extreme, and that's what this number here represents, is that if you go outside of the X space, like we were doing on the word graphic right here, if you go further and further out, there's only 1 more point more extreme right here than this point making a prediction in terms of the X space. Does that make sense? And I think what's confusing is you can leave one of the X variables right here. You could go down to a wind speed of 0. And so if you go down to a wind speed of 0, which should be this one right here, if you go down to a wind speed of 0, we can't even see that. So let's go to basically 0. You might not actually be extrapolating to the fullest degree right here. So this point right here is a pretty extreme point for the model to make predictions on. That's what this means right here. You're in the outer edges of the model. But when we were over here, we were more extreme. We were on there was only 1 point more extreme than us. Even though there's no points further over here to the left, it just so happens that in the multivariate sense, there would be, other points on the other side. So we have to think about this multivariate, how far are we outside the density cloud? And sometimes there's a gather up of points on the other side or an extreme point. And so this unique point over here is kind of breaking the density cloud of it. So even though we're outside completely here in terms of absolute distance, there's more points outside of here. So yeah, pretty complex topic right there. And if I can find it, let's do this. 3D. Let's make a 3D scatter plot with ggplot. Oh man. Plotly, cool. Here it is. I'm from Data Nova. We're going to do something super cool today. Awesome. Okay, here we go. So hopefully this code, okay, that's easy enough. Oh, that's super easy code. We can fix this. Okay. So if we're in the 3-variable world, so this is a really great talk on extrapolation now, because if we go to the 3-variable world, we have to use some more advanced graphics for this. So if we go to the 3-variable world, we have to use even more advanced graphics. A little bit. There we go. And let's take a look. So if you have questions, let me know. I'm going to go to the 3-variable world here and look at a 3-variable space. And I need to use this Plotly object. So let's bring up Plotly. Plotly is a great package for graphics. And we've got here the 3. You know what? I think they're using the empty cars data set. I think they are. Oh, no, it doesn't like it. DF data frame. Oh, they called it data. Oh, it works. So if this is all X variables, and we should see this right here. Is it working? Yes, it worked. It's got 4 variables in it, I believe. But the multivariate X space right here is even more complex. So we're doing some 3D graphics in R. Woo! I really want to take our data though and look at our data in the 3D sense. We don't need we can zoom in here if we want. But this is what's great about R right here is, you know, there's so many packages, so many cool things. And we can take our, let's look at it. Can we look at it as a prediction plane? I don't know. This is like, if you have questions, let me know. I'm just like, I love graphics. Graphics is one of my favorite things to do in R, just because visualizations are just lots of fun. We've got here color, so we don't have a color variable, so we're going to remove the color aspect of this. And then we'll remove the color argument from it. So remove the color aspect, and we need to remove this comma right here. Good, okay. And we'll keep that space. Plotly, data frame, so we're using my sample. Let me attach my sample. Attach my sample, there we go. Names of the variables, average humidity, average temp, average wind speed. And I think we're good. Title blank. Y-axis blank. Not gonna. I just want to look at the X space. It ran. Whoa! There's the multivariate X space. So here it is, right here, the multivariate X space. Looks like a mess. Is it? I wonder if it's CEX in here. CEX is character expansion. So if we're doing CEX, probably is going to be. I'm trying to think where the argument would go. Can I put that there? Add markers. I liked it. I didn't like that. No, it's mad about that. It doesn't like that argument. CX go here? No, it's not liking that. Where is CEX in this? Oh, it might be right here. Okay, that liked it. One might be the default, though. Oh, it doesn't like it. Well, B, where did CX? Let me look up point size. Change size of points. Change size of points in Plotly. Styling markers. Is this R or is this Python? Looks like R. No import numpy. Darn you, Plotly, for being both. Marker styling, R and Plotly. Size. It's just size, and it's under marker equals list. Add markers. Marker equals list. It's just size, color. Whoa, you can do that. Let me see that. There we go. That's it. It's just size. There's so many arguments to know. So many arguments. I kind of forgot how to explain interaction is. The way in which x1 explains y depends on x2 when x2. Yeah, let's take a look at that here in a second. You got it, Ryan. I'm just having some fun with this right here, trying to make this multivariate space. And you can, I think that's the extreme point we were seeing before. It does look to be that same graphic. We're in the viewer, so we'd go here to plots, and I believe this is the extreme point. If you look here, it's at 34, and over here in the viewer, you can see that point. We could look on it this way right here, and you can see, maybe it is. Oh yeah, no, that's it on the Z scale. That's its height on the Z scale right there. So you see, yeah, it's at 34. So that's that extreme point we were looking at right there. And I wish I could do like a density cloud on this to show as you go further out in it. But this is the multivariate 3 space. And this point right here looks to be the most extreme. You can kind of do an overhead view and take it down to 2 variables. But, and I think that's what we were looking at before. This overhead view, which kind of makes it a 2 variable graphic, is what we're looking at. It actually would be, I think we need to look at it this way. Some sort of flip and drawing of it would be the multivariate view, but love it. I don't know. I like graphics. Let's go look at an interaction right here. Let's close out of this plot. Lots of fun there with ggplot. Love ggplot. And just learn how to code, learn the arguments. So let's look at the interaction right here. Let's pull back up our interaction code. I'm going to put a cut in the video so we can talk about interactions. Talking about some interactions, let's do it, because we're going to talk about the way interactions explain data. So let's go take a look at that. Here we go. Okay, so with interactions, we need a model with interactions. We have one here. Here's our model with interactions. Let's make it look a lot nicer. We've got y tilde x comma data equals. We use the star to carry through model hierarchy. And with the star right there, we can visualize the model. We're going to expand upon this so we can see it really well. And let's rerun the code right here. And let's take a look. Now, when we have interactions, we need to think about the word depends. So we always say this: the way in which average temperature explains demand depends on average wind speed. So taking a look at this right here, when average wind speed is small, average temperature, it might be hard to see with this one especially, average temperature is actually going to have a positive coefficient. We can see that. So average temperature has a positive coefficient when average wind speed is small. Are you using, put your code in the chat right here. Are you making sure to separate out and not do the, so put your code and then make sure it's y tilde x comma data equals. So use the format y tilde x comma data equals, y tilde x, and double run it. Maybe you wrote it and didn't run it, but y tilde x comma data equals, and it should look like that right there. Y tilde x comma data equals, y tilde x comma data equals. And so the interaction coefficient is actually going to be positive here. The interaction coefficient is actually going to be positive. And how do I know that? It's a little hard to see, and I'll probably do a stronger interaction here in a moment because this is a very weak, non-significant interaction, which is all right. We can still talk about it. But if you notice, when we go to a higher average wind speed, the line has a higher slope. So make sure to use the format y tilde x comma data equals, y tilde x comma data equals, and don't include the names of the data frames. Y tilde x comma data equals. Make sure to have the y tilde x comma data equals. And so if the data frames are in there, it will look weird though. Like you want y, your y variable. So the name of the y variable, the name of the x variables, and then data equals right here, y tilde x comma data equals. And you can always use the attach function. If you've written attach, then it'll auto-complete these right here. If you've done the attach function, which is just attach my sample. If you do this right here, my sample. If you do this right here, then when you type things like demand, it will automatically look up the variable and do the autocomplete. Ah, no, that's all right, Ryan. This is why we're here. This is, people will look at that for an hour tonight and be like, they'll be like, I have no idea. So Ryan, 50 points. I appreciate it. Just tell me when something doesn't work. You're doing the exact right thing by asking these questions right here, right now, being like, hey, this doesn't work. Hey, can you explain this? That's exactly what we do in office hours. Thank you, Ryan. Great job. So what we notice here is there's a positive interaction. And how do I know that? I know it's a positive interaction because when average wind speed is small, there is a positive relationship. But do you see this red line? Is this red line steeper or less steep than the blue line? So Ryan, is this red line right here? It's hard to see, but it starts out down here and it's like catching up to the blue line. Is the red line steeper or less steep than the blue line? Is the red line steeper or less steep than the blue line? So is the red line steeper or less steep? So this red line here, is it steeper or less steep than the blue line? I think it starts out lower and then it's like catching up to it. So eventually, if we went further out, it would eventually pass the blue line. It's steeper. And this is when average wind speed is larger. So when average wind speed is larger, the coefficient for average temperature will be wetter. When average wind speed is larger, like as average wind speed goes up, the coefficient for average temperature will be wetter. So when average wind speed is higher, the coefficient for average temperature will also be wet. Because here's where average wind speed is smaller, but if average wind speed is higher, it'll be larger. So we can see this in the output that there's going to be a positive coefficient. Average temperature will have a positive coefficient and the interaction will be positive also. The average wind speed is going to have a negative coefficient though. So average wind speed has a negative coefficient, and then as average wind speed, or excuse me, as average temperature gets larger, it actually gets less negative because there's a positive number, but average temperature has a positive coefficient here. And as we go to higher average wind speeds, it's also going to become more positive. Probably, let me see right here. Trying to find a really strong one. Yeah, that's pretty good right there. So take a look at this one right here. We've got a really strong one, or really apparent. Oh, and this is significant. So take a look at the graphic on the far right. With the graphic on the far right, what do you notice? Effective average temperature has a what coefficient when average temperature is small? Effective average temperature has a what coefficient when average temperature is small? When average temperature is small, effective average temperature has a what coefficient? When average temperature is small, effective average temperature has a what coefficient? So when average temperature is small, as a positive. But as average temperature gets bigger, effective average temperature will have a what coefficient? It's hiding behind there, but so as average temperature gets bigger, effective average temperature will have a what coefficient? Negative, exactly. So effective average temperature in the output is going to have a positive or negative coefficient. Do you think effective average temperature will have a positive or negative coefficient? Effective average temperature will have a what or what coefficient? So effective average temperature will have a what coefficient in the output we look at? Just effective average temperature, it'll have a what coefficient? It'll actually have a positive because it starts off positive right here. And then that means the interaction is what? So effective average temperature will have a positive coefficient. Do not worry about anything wrong. Don't worry. It'll have a positive coefficient, but the interaction is what? Because the interaction it has with average temperature is causing it at larger values of average temperature to be what? So it's going to have a positive coefficient to start, but then the interaction is going to be negative. So let's go ahead and look at that output right here and confirm that effective average temperature has a positive coefficient, but then here's effective average temperature. The interaction right here will cause it to be more negative. So it starts out positive. That's the blue line right here, or close to, somewhere around there. This is for very small values of average temperature. It's going to have a coefficient close to this, or for an average temperature of 0, it would have a coefficient of this. But as average temperature goes up, it's going to become weaker, and you see that right here, it becomes weaker, till eventually at a high enough average temperature, it's going to have a negative coefficient. So what way, this is a big question, in what way does effective average temperature explain demand? Effective average temperature has what relationship with demand? Effective average temperature has what relationship with demand right here? So what kind of relationship does effective average temperature have with demand? What kind of relationship does effective average temperature have with demand? There's a very quick way of saying it. What kind of relationship does average temperature have with demand? Effective average temperature have with demand? Well, so the relationship effective average temperature has with demand depends on average temperature. The way in which effective average temperature explains demand depends on temperature because of the interaction. When average temperature is small, effective average temperature has a positive coefficient. When average temperature is large, effective average temperature has a negative coefficient. So just look right here. When average temperature is small, it has a very strong positive coefficient. When average temperature is very large, it has a somewhat strong negative coefficient. Does this make sense here, Ryan? Does it make sense to talk about the idea of it depends? Like, in what way does effective average temperature explain demand? Well, it depends on the average temperature. When the average temperature is small, it has a strong positive coefficient. When average temperature is large, we can also see that over here. When average temperature is large, the interaction comes into play, making it a negative coefficient. Like eventually this will overtake when you solve it mathematically, because every time average temperature goes up by 1, the coefficient will go down here, mathematically speaking, by 7.27. Does this make sense here with the interactions, Ryan? What are you thinking about it? What questions do you have? Let me know. I really want to update channel. Release testing. What is this? There's a lot of things I want to try with the OBS, but it looks like we've streamed well today. It looks, or at least with this, so maybe I'll do this for class. Maybe I'll try this out for class today, and I'll see if class has any issues. So tired. Semester's so far. What questions are there? I'm gonna look at one thing right here because there's something I've always asked questions if you have them. I'll hop to space while we're looking at this. Ask questions. I think so, but for the assignment or the test for the interpretations, would we only talk about you? You can. I put a little music on. You can talk about either X. Like maybe one might say on the test, it could say like, explain the interaction in terms of the way effective average temperature explains demand. Like explain the interaction with respect to this. The idea with interactions though is that one coefficient depends on the other. And it is true that that other coefficient depends on the other coefficient. So it is true that effective average temperature's coefficient depends on average temperature, and average temperature's coefficient depends on effective average temperature. So it's vice versa. They're like really good point right there. And on the test, I try to make it clear which one I want you to explain. And that is a tougher question on the test. It's a question that definitely takes looking over the output to where it's like, okay, wait a minute. Wait, I've messed it up now. Can I do that? Transform. Don't flip. Center to screen. No. Transform. There we go. Now I'm in the center of the screen. Let's see if I can find. There was something I wanted to look at. Set reference level in R. How to force R to use a specific factor reference level. Accept cookies. That's interesting. Wait. Within DF. What? Relevel. What does the within function do? DF by using the relevel function. Because a data frame variable B GL. What does the function GL do? So many functions I don't know. GL. I think it's creating groups. 5, 20. Are they doing that as a factor? Is a factor. Huh, GL. Let's take a look at this. See if there's questions here in the chat. Have you already gone over it today? Oh, yeah, Taylor, we can totally do that. We've gone over it some. What questions were you wondering about on that, Taylor? Thank you so much. I'm looking up some stuff here as we talk. What were you wondering about extrapolation, Taylor? Feel free to ask. Let's hop back to the main screen. Taylor, let me know your questions on extrapolation. I was going to try something here. I was going to try something. Trying something for the new assignment. So let me know your questions on extrapolation. So I think, yep, we got Ryan's questions. Great job, Taylor. Feel free to let me know. We'll head back to extrapolation here. And so I want to make a model predicting tip percentage. I should only understand how to run the function. Yeah, here we'll go. Let's talk about that now, and then I'll come back to this. Let me do a cut in the video. You ready? So that way we can know where this is at. So let's do some extrapolation. Let's talk over extrapolation. Let's go do it. So when it comes to extrapolation, and we were talking about like the multivariate sense, to predict. Okay, here we go. Got a big to predict right here. And let's take a look. Okay, there it is. Let's move it around. I always call this DF. I'll explain why I call that DF right there. I just like to call my data frames DFs. So that way I can just go right here and type capital DF. Petrie uses he uses new to predict in his. So you've got some values right there. This looks like it could work. And you're using these two values right here. You're using average temperature. Okay, cool. Yeah. This looks like it could work. Yeah. So Taylor, you've done it. You've done a great job right here. The values you've chosen are all right. You could just round these to like 430, and these are average temperatures in degrees Celsius. So you can just round them. These are wind speed or effective average temperatures, which are very similar. And so you could just do that right here, and we can check the extrapolation check. So they're very similar. And what you've done right here is you're looking at like, and here I'll visualize this for a moment. Let's bring in this first point a little bit more. Let's we need to probably raise the temperatures. Okay. So let's look at where this first point is at now. Really? Average temperature, effective average temperature. What is the means for these data sets? Summary of my sample. And let's go take a look at it. I'm going to find out about this data right here. So this will tell us what the means for the data are. There we go. And really, that's outside the space of it. 12 and 12. That's weird. Wouldn't have expected that. 30. What? 21. Wow, what is it? It's because of that outlier, I think. Wow, that outlier is really messing with the X space of the data. Let's go look at the X space of the data because this is such a weird X space. What I'm going to do is I'm going to create a model right here from the X's. So creating this model right here, we're going to use these two variables right here as our model. And so we're just going to take these two. This is kind of a really deep talk on extrapolation right here to talk about like what's going on and when we'd be extrapolating. So here's our model. And this is why if we slightly even leave this X space right here, we're extrapolating. So to not extrapolate, we would need to be, and look, like this point is the furthest out point. That point is just craziness. 15 effective average temperature, about 10, that should be in the X space. So 15 expected average temperature, or effective, and then about 10 on the other one. And that should be within the X space now. I'd be shocked if it's not. Wait. Oh, because I've stored the other model. Let me go here with this. Create the model. Oh gosh, no, stop it. Ah, there's my 3D plot. And then let's talk about what's going on here with this. That's still at the edge of the X space. Can I... Instead of 3 observations, I only got 2? So you're not getting... Are you not getting that output? You said you only got 2. You should get 3. You should get, for the 3 points you're predicting on, the first, the second, and the third. And This is a weird X space for the data. If you notice, this point right here is one of the only points outside. Here, I'll show you what we mean by that. Let me go to 20 and 15. I can tell you what this is going to say here. There's 413 points of data that are inside the cloud, so we're going to get 99.8 when it rounds. I'm going to predict here for 15 and 20. So 15 and 20. And now when I run this, and we need to use the correct model, we get this 99.8. So I want to show you where we're at. Take a look at where we're at right now. We're at AB line horizontal equals 20. And I want to explain what these numbers mean because it's very hard to stay inside this data set. And vertical. Oops, wait. There we go. So this is where we're currently at. Being right here, how many points, like if you think about going outside of this data right here, how many points are further out from when we make a prediction right here? So making a prediction right here, how many points are further outside of this cloud of data right now? Like just right here, and then I'll show you the calculation I did, because how many points are further outside of this? Like if you think about, if you predict right here, in terms of this multivariate X sense, because that's what this is returning now, how many points are further outside of where this prediction is being made? This is where we're predicting on. This is the combination of 15 and 20. That's where we're making a prediction using X's of this value. How many points in the multivariate sense are further outside of this? So if you were to go outside of this X space in like a multivariate sense, how many points are further outside of it? We could try to re-enter the X space after this. How many points are further outside of this? How many points would be, if you look at all these, it's just the one. Great job, Taylor. Great job. It's just the 1 point. So it's just the 1 point. So since there are 414 points in this whole data frame, do you see how I know there's 414 points? That means there's 413 points inside of it. And guess what we get right here? That's what we get when you round it, 99.8%. 99.8%. And we could try to, let's do this. We're going to take right here, and I'm just going to kind of draw this out so I can see where we're at. If we drop this down to 10, see that's we went too far below. If we go to 11, so it needs to be more like 12. And now we're inside the X space again. So if we bring this here to 12, and now we check the extrapolation check, what's it mad about? We don't have the right model in here right now. And look, do you see now, this is at 69.3 because we're inside of the X space. If we move up this way, we'll actually go to smaller values of extrapolation check. Is this making sense right here? Now we're inside the X space, but what happens if I go a little bit up here maybe? Like if I go up to like, let's take this and go up to about 15 or 14. And we still have the wrong data right here. I need to put this up higher so I stop switching models. There we go. Let's put it up to here. And that way we won't switch models again. If we do this again now, and we visualize it. Ooh, what's going on? Where's my visualization? Because I didn't change models yet. No, we do want it down here. What am I doing? Yes. So we want it right here. There we go. Now we're slightly above it. Does it matter how many variables are in assignment 9 multiple? Nope. You can put as many variables as you want. Great question, HCT, and great job working on that right now. And this is the average temperature. So now when we do the extrapolation check on this, we are actually pretty much outside the data. Well, it is the bivariate sense. So it is the bivariate sense. This is the important part of it right here, Ryan, which is hopefully not too confusing. But when it comes to extrapolation, it's not just, because if you look at this, this is not that extreme in either value. But the reason that this is an extrapolation is because it's leaving the X space of the data. And this one right here, let's draw this out. I can reappear on the screen. This one has a very tight X space. So drawing out this X space of the data, the reason you're getting extrapolations here, because this is a really good like example of it, is the lowest amount of extrapolation would be in here. That's like where no extrapolation is. And then you would go to some degree of minor, not really extrapolation, but further outside the data. And then you would go to, here, we'll redraw that in a second. And then you would go to extreme towards the edge of the data frame right here. And that's where extrapolation is really starting. And we need to redraw this. Really? I can't draw over that? Well, I guess it's behind the scene. So the further out you go, the more you're extrapolating. The further out you go, and that's why a point like right here, this point is not that unusual in its x2, and this point is not that unusual in its x1. This point right here actually might be towards the mean of x2, but this point would come back as an extrapolation of what? So even though this point right here is not that unusual in its x1 or x2, it's a little low in x1, and it's kind of the mean of x2, because the mean of x2 might be somewhere around here. Mean of x2 could be right about here. That could be x2's mean. And the mean of x1 might be about here. So if you look, it's right above the mean of x2, and it's right below the mean of x1. But why is this point in extrapolation? So we use, so we say we are extrapolating on the extreme value, since it's well, not just the mean of the, so it is sort of like the mean of the x's, but sometimes x's can make like a weird x space. It's sorry, it's so complex. Like, this is such a complex topic. Things that we are extrapolating on are unusual in their x's or their combination of their x's. Does that make sense? When we are extrapolating, it's because things are unusual in their x's or their combination of x's. So this one right here is not that extreme in its x1 value and not that extreme in its x2 value, but it's very unusual in its x1, x2 combination. It's not that far away from the mean of either. It's actually super close, and we can make it even closer. Now it is the mean of x2. Does that make sense? How this is at the mean of x2, but actually its x1, x2 combination is very odd in terms of what we have our data on. So we'd actually be extrapolating, and that's what's happening with this model right here. Does that make sense, Taylor? Like, this is only a little low in x1. It's at the mean of x2, right about at the mean of x2, but its combination of x1, x2 is very odd. We would not be extrapolating if it was down here, and now it's actually more odd in its x2, but it follows the x1, x2 bivariate combination, so our model is actually trained on data that follows this pattern. Once we move this back to the mean of it, even though it's a more usual combination of x2, we'd be extrapolating. You can use extrapolation check. Hopefully this graphic here and everything is literally as deep as we can go on this topic to understand that, because once you leave the bivariate sense, you go into the multivariate sense. Oh, no, I just clicked Streamlabs. Streamlabs, go away. You could do crazy things, Streamlabs. No, we're not using you today, Streamlabs. It's going to take a while to know not to click Streamlabs. Then watch me accidentally close out of this and be like, shut down the stream. So what we did earlier, and we won't go into too much detail on this now, is we actually talked about the multivariate 3-variable sense, because this is why it just gets to be too complex of a topic, because if you now go to the multivariable 3-variable sense, you're actually going to be talking about like a multivariate sense right here, and this is all being done via R. But this, now you're in a multivariable 3 sense, so like over here, what percent of the data have you gone through? So now, can you imagine an egg right now? Like, pretend this is a weird egg right here, and the center of the egg is like the center of your x's, the mean of your x's, and then the further out you go outside of that egg is the more you're kind of extrapolating. So in this multivariate 3-variable x sense and then 4-variable x sense, that's going to get even harder to visualize. But this would be the idea of, on a 3-variable x setup, to what degree are we extrapolating? But we could visualize this, and we could talk about this area over here, which it looks like there's only one more extreme value. So this would be towards the edge of the multivariate sense, the multivariate field, but it gets more complicated. So that's why we have extrapolation check, because it breaks down all the algebra, the eigenvectors and eigenvalues for us. But the two variable sense is much easier to understand when we talk about extrapolation. We did a few graphics of that today, and you can see it matters about the combination. Here's how far away you are from the mean of the x's right now. But if you were to take this same distance and turn it to a different orientation, you could very quickly leave the x space. You're just as odd. And you're not that low in x1 and you're not that low in x2, but the combination here is very odd, where previously this distance right here was not that much of an extrapolation. HDTS, do we use ANOVA multiple model to run the partial F? Yes. Well, you won't use it on multiple model, and we did a little bit of this earlier today, so I'll show the code. Great questions, HDT, and I love 3D graphics. We made that earlier to talk about the multivariate X space, but yeah, really cool for instructional purposes. But you know, you can put it in an HTML document. And feel free to ask questions. You will use the ANOVA, and you will use ANOVA, comma simple model, comma full model. And here I can do one right now. If we want to see if something brings more information, we'll do it right here in assignment 8, even though we're not doing it here. We have a complex model and a simple model. So let's say we take the simple model. Here's the complex. You can call it complex. You can call it multiple. Any sort of naming conventions are fine. Go font bigger. Go font bigger. And so let's bring this down to one variable. And we'll call this simple. And we'll call this complex. And let's talk about what we have right here. Complex. There we go. Okay. So what we have right here is a comparison between two models. So when we run this, we need to create a simple model, and it can be as simple of a model as you want. It can be a one variable model, a two variable model, doesn't matter. Simple just means has less variables in it than the complex model. So the simple model is just the smaller model. That'll be our first model we input into the partial F, will be the simple model. The complex model will be the model with more variables in it. So this one, by virtue of having more variables than the simple, is the complex. That's the definition of what we call simple, less variables, then complex. Complex, more variables than simple. So when we do the ANOVA, we go simple, comma, complex. And in the ANOVA, we want to see if adding in the extra variables, which if you notice, there's two extra variables. Wait, for the multiple model, do the interactions. Yeah, you don't need to do interactions. You could if you wanted. You don't need to, though. No, great questions. And definitely let me know if you disagree with the graders on anything. There's a lot of avenues to go. A multiple model can definitely have interactions. You don't need to. You just kind of need to examine this. And then the key thing is to know to look at what right here. So HGT, if you're looking at this, there should be something that jumps out to you immediately. And you're like, oh, that jumps out to me. And that tells me this. Like, what would I learn from this output? What would I look at with this output and be like, okay, that tells me something. What do I know from this output? Like, what's the point of this output? Like, we're always asking, what's the point of this? Why are we doing this? What are we learning from this? What knowledge have we gained by doing this? We could look at this. That's good, or this is even better, because that's standardized. That is the standardized reduction in the sums of squares. This is the difference between the amount of variables between the models. There's two. You might say, well, why is there two? Well, because it looks like there's only one extra, but we have the interaction. So the interaction plus the single order term carrying out model hierarchy. Just so we can see this real quick right here. The simple model just has the one variable in it. There's the one variable. And the complex model has in it the two extra variables, the interaction along with the simple term. And let's take a look. What you doing? There we go. What does this output tell us right here? We see that there's a difference in 2 for the number of variables in the model. We have your average temp, effective average temp, and the interaction between the two of them. We see here the reduction in the sums of squares. We see here the F statistic, which is going to be the standardized amount of variation we observe being explained over what we would have expected via random chance. 18.3 is kind of high, but we don't always look at that because is 18.3 high? Well, it depends on which F distribution. And I wish there was a 201 student here because when I say which distribution, they would know degrees of freedom. We were talking about that a lot today. So the F actually has 2 degrees of freedom for it. So we have this right here. And is this high? Is this a lot of reduction right here, HTT? What does this tell us right here by looking at this? I'm going to try something. Yes. What? Oh. 1? Really? It just, oh, that's all right. No worries, HTT. Great answer right there. 50 points and everyone else watching. I do not mind when people say they don't remember. That's a perfectly fine answer to give. So the null for this test, if you think about it, null and alternative, the null for this test is that the new variables do not bring any new information. What are you going to do to the null right here? So the null is that the new variables, the complex model does not bring with it new information. What are you going to do to the null? What are you going to do to the null hypothesis right here? What will you do to the null hypothesis? So what will you do to the null hypothesis? So the null is that the new variables do not bring with them any new information. So going from the simple to the complex, the null is that there's no new information brought by the complex model. You're going to reject it. So what does that mean the complex model gives us? The complex model gives us what? Be really interesting. The complex model gives us what? Let me see how that's... No. New information, exactly. So should we use the complex model or should we use the simple model? Oh my gosh, what have I done to my digits? That's what happens when you mess with your digits. Should we use the complex or should we use the simple model? Should we use the complex or should we use the simple model? And the answer lies in the ANOVA, because the ANOVA is telling us if we go from the simple to the complex brings with it new information. Exactly, we should use the complex. That's what this p-value right here represents, is the comparison of this model to this model, whether this reduction in sums of squares is statistically significant, which is what we're trying to do. We're trying to explain the y variable, and that is a large enough reduction in the sums of squares error to be statistically significant. So this reduces or explains more variation in such a significant way that it's unlikely due to random chance, and thus we would say, yes, we have reason to use the complex. We have statistically significant evidence. And so that's how we can compare model 1 versus model 2. And right here, you actually see an ANOVA, but this ANOVA always compares our model to the what? Like this ANOVA down here, which has an even smaller p-value, always compares our model's reduction in the sums of squares to what? You see higher F statistics, smaller p-value. So this ANOVA down here on the bottom will compare our model, the complex model right here, to the what model. So this ANOVA down here on the bottom of the screen always compares our full model, our complex model, whatever this is. It could be the simple model. It always compares this model to the what model. It compares it to the starting out model. So I think like the starting out model, the no variable model, this is actually an ANOVA comparing our model to the what? Not in this instance, not the simple. This p-value compares our model to the naive model. So this one compares our model to the naive model. So this will be our model versus the naive model. This down here in the partial F, when we run it with the simple versus the complex, we'll compare it to the simple model. This compares simple to complex. This ANOVA as a full ANOVA compares it to the naive model. We should be able to do. And there's the p-values for the individual variables, but if we go here and we can calculate the sums of squares from that, I wish it would just show us, it shows us the individual variables. And yeah, it's doing the individual variables there. And it does it a slightly different way on the calculations. Yeah, slightly different. Is it carrying one more digit on that? That's interesting. Oh, and the ordering matters, yes. And that's why that last one's the same, because on this one, the ordering matters. Yeah. So it's pretty interesting right here. And I wish it would just give us the full reduction in the sums of squares, because we should be able to get, let's see right here. I guess it would work. Let's see, right. Let's think about this for a second. Brian's brain is thinking. So we have here all the individual F statistics. We have here the mean sums of squares. We have the sums of squares. And so we have what is being explained by the X's. So we should be able to get what is left in the residuals, what is explained by the X's, there's that. And we're doing this over 3 variables. There's that. And there's the mean. So it should just be the ratio of these, right? Yeah, there it is. 81 point, and there it is right there, 81.6. So don't worry about how do you create a new variable? Yeah, let's do that next year. Let's do that. I'll put a cut in the video and we'll talk about creating a new variable. So this right here, this 81.6 is the comparison of how well our variables are doing on average, which are the variables right here. I summed those up and then I divided it by this. Have to go, oh no, awesome. I'll put this in the video for you, HTT. So check this out later. I'll go ahead and explain how to do that. I was just doing some F's table calculations, which we do not have to do in this class so much. Awesome, no worries. Let's put a cut in the video. We'll put a cut in the video right there, and let's go talk about how to do some variable creation. Let's go talk about variable. Okay, so with variable creation, let's open up a new sheet, and let's just talk about this real briefly right here, how to create variables inside of R. So if we're working with my sample, and we have a variable like average temperature, we can take and do a ratio. We can do whatever variable we want. We could divide it by effective average temperature. And this right here will create just a new vector. Now, what we usually want to do is we want to store this. I'll store it into X for the moment, because now I'm going to take and go to my sample. And you could do this in one step, but sometimes if the code gets too long, I don't want to do it in too many steps. And let's just call this new variable. So that's just going to call a spot. And if you look at my sample now, what do you notice? At the very end right here, we have new variable. You can call it whatever you want, but this is just, and you could have just taken all of this right here and run it like this, and it would give you the same result. It's just sometimes nicer to put it in 2 steps where you store it as something and then store it into something. We can then run the head on it, which is going to give us just the first 6 observations to show that we have it. And let's go here to new variable, and there's the head of the new variable to show we've created it. Is this new variable a good idea? I do not know. Let's find out with a multiple model to see if it does any good. And we'll go right here to demand tilde dot comma data equals and mass sample. Let's run it and let's do a summary of this and let's see if it did anything. What? No way. That variable's super significant. It's one of the top most significant variables, even better than average temperature and effective average temperature. What? No way. I have to tell Petrie about that. Oh, multicollinearity took over on that. It's probably because it's created from it. It can't. So there's no, the multicollinearity right there. That's it's a singularity you hit. So the new variable can't actually do that. Where we had like 45% R squared, 50%. You know what? Let's check it out. Let's go squared model and sets everything squared. We're doing partial F again, and let's go right here to the model. Let's go linear, and let's remove that. Let's go here and let's compare them. So the partial F can be used to compare these models to see if we should square it. And so we're back to doing a partial F now, right back to partial F. And the answer is, hey, at least some of those should be included. The inclusion of the squared terms added new variation unaccounted for, and there were 9 new terms added in. So we can see there were 9 new coefficients added to the model right here. Here's the reduction in sums of squares. Here's the standardized reduction in the sums of squares. And yeah, and the variable alone, the new variable by itself, did bring with it new variation with the other variables already included, and I just randomly divided those variables. There's the new variable right there, the division of the variables, and who would have thought? Just mind blown by that. I had no idea. I wonder if it's due to the outlier. Let's, the outlier is 337. So let's remove the outlier here and see if the outlier is drastically impacting this. The outlier did play some role in it, but it's still significant. The ratio of the two. And let me look at that variable alone now. So now I just keep having questions. I keep wondering about this. Let me look at the linear relationship. Yeah, it's super significant by itself. And so this is all variable creation right here. This is all just creating a new variable and then investigating it. I'm removing the outlier just because I don't want to see the impact of an outlier. I could include it. If I don't have good justification for removing the outlier, I shouldn't remove it. There's definitely, I mean, there's a linear trend, but then there's things that break the linear trend. This is going to have a huge issue with the check regression. The normality or the linearity is going to have a major issue. And the normality, we're going to have some problems. Yeah, we got problems. The equal spread has a problem. The normality has a problem. The linearity has a problem. That's weird. Those variables are close. Aside from that, it's really good. It's not a bad model. And these points would bring it down. So it has a better, it's tight right here. I don't know. A lot of interesting stuff with this. And that's so weird why these points over here. I wonder if we do an interaction. I don't know. It's all the big questions. If you have more questions, let me know. But I have a question. I'm trying to knit my worksheet and it won't let me because it has an error on 108. This is my code. Send it to me send it to me via my sample rows 1 through 5. Check to see if rows, so if it's crashing on that, but it also will say this. Do this, Kelly, because I know we're on Discord together right now, but it says rows are not found. So you might want, I think you're trying to look at 337, right? Before this line of code right here, are you trying to look at 337? Store into here 337. Add that right here. So I probably just got the same thing, rows not found. So make sure whatever rows you're looking at, Kelly. Thank you, Kelly. Great questions. Let's throw some 50 points. Does that work right there, Kelly, adding that in? So does that work for if you put that right before it in the line of code? So right before it, make sure you have rows and save into it whatever rows you want to look at. You could do a vector of rows, like rows 1, 3, 4, whatever. And then you could do this and it'll print multiple rows. So whichever rows you're trying to look at, make sure those are there. But in our assignment, you're probably looking at 337. You're probably looking at that row. So you could do multiple rows by concatenating a vector, or you could do one row and we have concatenate or what is that called? What is it? Combined. It's also called combine. I should just call it combined. Concatenate just sounds crazy. Did that fix it, Kelly? How does that look? Thank you, Kelly, and everyone. Great questions, Dan. I don't think we've buffered. So does this mean I'm now using this at all times? You're welcome, Kelly. Thank you for swinging by. That's the point of the office hours is you combine and say, hey, this doesn't work. This is, what's really crazy. I'll put on the music right here. We'll hop to space. Let's do it. Here, put on. Yeah. Hop to space. What's so crazy to me is years ago, I actually would have students like, I would be sitting next to them and I would have them send me their code and I'd have to work with it. But now after like 6-7 years of working in R pretty much every day, not literally every day, but like pretty constant, someone will say they have a problem and then I don't know, I've seen a lot of problems. So don't worry, I've been through this. I've been through where the code just doesn't work and you're like, it doesn't work. It's not working. What's going on? And then you have to be like, okay, if that's not working, we need these components. It's like making a recipe. It's like you wanted to bake a cake and you didn't put the eggs in. I'm like, oh, we need the eggs right there. So I just want to bake. We got so many cake mixes that we keep talking about. We need to bake a cake, and I'm just like, let's do it. And then you're just gonna see Brian one day just sitting here eating cake, and I'm just gonna be like, yeah, we got cake. Right now we got ham though. Had ham this weekend, so we just got a bunch of ham. That's the way it goes. I think that's got it. We'll see if you have questions. If you're here, ask questions. I'm gonna go probably eat some lunch, respond to some emails. Everyone's doing a lot of hard work. I appreciate it because that's what it takes. Hard work, practice. The background's not stuttering anymore. The stream's not stuttering. You're welcome, Kelly. Great job. Great job. I guess everything might work over here better. We're streaming on OBS now. You're welcome, Ryan. Great job, Ryan. Let's throw another 50 points. I don't care. We'll throw some 50 points. Let's do this. Put on one more song. This song's long enough. With that, everybody, great job. I think my final button works right here. Let's see. I'm gonna do some tests. I'm gonna finish the stream and let's see if it works. You ready? Bye for now, everyone. Bye. You guys can still hear me? Yay! Yep. Music is still playing. I know you can still hear me. And now you won't be able to hear me in 3, 2, 1.